Welcome to Ready to Derive. In this video, we're going to learn about the technique of integration by parts. But you should be familiar with the other integration technique, U-substitution. So when would you use U-substitution? Well, a situation like this, where you have e to the x squared, which is a composite function, and you see that x hanging out outside there is a form of the derivative of x squared. So when you have a situation like that, you know you're in U substitution land, and what you need to also appreciate is that U substitution basically is the integration technique that undoes the chain rule, which the differentiation technique of the chain rule. So what looks different for integration by parts? That's where it looks very similar, except here we have x, e to the x. There's no, x is certainly not the derivative of that x up there. It definitely looks like we have a product here. I mean, we had a product here, but here we can't relate the two functions. This should be sort of an instant suggestion that you're going to be using technique of integration by parts. And what you need to know about this technique is that it is the reverse, or it undoes the process of differentiation using the product rule. So without further ado, let's begin. So we're going to begin by deriving the integration by parts formula. And to do so, we need to start with the product rule, which says this, that the derivative of a product of two functions is the derivative of the first times the second plus the first function times the derivative of the second. So if we think about it, derivatives and integrals are inverses of one another. So if you take the derivative of a quantity and then were to take the integral right afterwards, you would get back to the original quantity. So that means that basically if we take the integral of both sides, we'll undo what's done on the left. So the right-hand side will be the integral of that expression, should just get us straight back to the product fg. Now we're going to apply property of integrals, which states that we can rewrite that integral as the sum. So the integral of the sum of two functions is the sum of the integrals. And then we're going to isolate this here. And I'll explain why in a moment. We're going to isolate this by subtracting from the other side, the other quantity. So we have the f of x times g of x, and we're going to subtract that to the other side. And this right now is our working formula for integration by parts. There is a more efficient way to write this. We'll do that in the next slide, but let's just use this format once before introducing that. So we're going to take an example, and we are going to find the integral of x e to the x. Now, notice that we have to kind of define f and g to be one of each function. So we're going to make f this function here, x. I'm not sort of explaining why now, but you'll learn why shortly. And we're going to make g prime x e to the x. So when we do that, we have, so f of x is going to be x, and g prime x is going to be e to the x. Well, naturally, if we have those, we can figure out these. So f prime x, the derivative of x is 1, and the integral of g prime x, which is g of x, will just be e to the x again. So according to this rule, then, so we have, let's see, we should be able to get this by doing f of x, which is x, times g of x. So g of x is e to the x. And then we have minus the integral, and f prime is 1, and g of x is just e to the x dx. And so x e to the x is done. And then we just have to take the integral of e to the x, which is just e to the x plus c. And we're actually done. Now, if you want to check that and make sure we did it correctly, let's see what happens if we take the derivative of this expression. So the derivative of c is 0. The derivative of x e to the x by the product rule would be 1 times e to the x plus x e to the x. And the derivative of e to the x here would be e to the x, right? And this would be 0. And then we see that when we use a different color, we see that this e to the x cancels with this one. We're left with x e to the x, which is what we had originally. So now we're going to introduce the alternate notation, and just a little sort of more compact way of writing it. And you'll probably have seen this, in your classes or in your textbook. What we do is we make u equal to f of x. So we're going to replace f of x with u, which if we take the derivative of that, say, so du by dx equals f prime x. And if we just write that as a differential, we've done this before in U-substitution, is we can just multiply the dx to the other side, and we have that. So hold on to that expression. We're going to make v g of x and go through the same motion. So dv by dx is g prime x. So dv is g prime x dx. And then we're going to look to make substitutions. So I think I just might use white here just to clarify. So f of x, okay, that's u. Now g prime x dx, we're going to treat that as a quantity, and we're going to realize that that's going to be replaced with dv. And f of x is u, and g of x is v. And here we have to be a little more careful. So if we see, so g of x is v, but we're going to pair f prime x with dx, f prime x dx, and replace that with du. So this becomes, more compactly, the integral of u dv equals uv minus the integral of v du. It just has kind of a natural ring to it, which makes it easy to remember and a lot less cumbersome to write. So let's do another example. Say x cosine x dx. And again, you're sort of having to, there is some art that goes into choosing which one is u and which is dv, but we'll treat that in a moment. Right now, let's go with what we did before. Let's just make u, the first function, let's make u equal to x, and we'll have dv, so this is going to be u, and that means now dv, the whole thing is going to be cosine x dx. So I'll write that here. And then when we write du, so du by dx would be 1, so du is just dx. And if we integrate both sides, the integral of cosine x is sine x. And by kind of taking the integral, we're left with v equals sine x. So then we get to use the formula. So u times v, so u is x, v is sine x, right? So we just replace that, and now we're going to do minus the integral of v, which is sine x dx, right? Because du is just dx. All right, so now we get to do this. So we'll carry the x sine x down, and the integral of sine x is negative cosine x, which would make this plus cosine x plus a constant. And so technically, that's our answer. But if we'd like to check that we did it correctly, once again, we could take the derivative and make sure we get back to the original integrand. So this should feel familiar now. So this would be the product rule. 1 times sine x plus x times the derivative of sine x is cosine x minus sine x, because the derivative of cosine x is negative sine x, and then plus 0. And once again, we have sine x canceling with sine x. We're left with x cosine x, which was our integrand to begin with. Let's talk about how to choose which function is u and which piece is dv. So let's take the integral of x cosine x dx again. Here's the formula, and this time, though, remember we made u equal to x the first time around. Let's try making u equal to cosine x. And then dv would be x, and don't forget the dx. All right, and then du, so that's not too bad. The derivative of cosine would be negative sine x. And v would be the antiderivative of x, which would be half x squared. Notice we don't need plus c or anything like that because there's still an integral in the formula. So we never need the plus c until the very end when all the integral signs are removed. Okay, so if we use the formula, so we would do u times v, so that would be cosine x times half x squared minus the integral of v du. And v is half x squared, and du is, sorry, I should put dx there. Du is negative sine x dx. I'm hoping that you can already see, maybe if we tidied this up a little, hoping it might help. So we put the plus, you put the half out there. We have the integral of x squared sine x dx. That feels worse than what we began with. So the overall goal in terms of how to choose u is to make sure at least that you obtain a simpler integral than the one that you started with. And here, this is definitely not a simpler integral. But there are some other guidelines. So in terms of like order of preference. So the order of priority for choosing u is u will always be, if there's a logarithmic function, u has to be that. And the reason is because if you make that dv, well, you don't know how to integrate a logarithmic function. But if you make u, ln x, then du will just be 1 over x dx. Not so bad. So you have no choice. Similarly, if you have an inverse trig function, like inverse tan x, you don't know the integral of that, so you've got to make that u so you can take the derivative. The problems we considered before, where u was x, that's sort of, it's called an algebraic situation. So that's if u equals x, or x squared, or rad x. Then the trig, that would be, so you would make u equal to sine x or cosine x, sort of only as a last resort. And exponential, so u equals e to the x or 2 to the x, that would be the very last resort. So some people remember that by, let's see, I guess the letters it starts with. So liat, I don't know why that's useful or if that's easy to remember, but that's kind of L-I-A-T-E is the order in which to choose u. So moments ago, I said we would have, in terms of order of priority, we would have to make u equal to ln x because we don't know the integral of ln x. But thanks to integration by parts, we are going to learn what the antiderivative of ln x is. So following the instructions from before, we are going to make, so u, the order priority is u has to be a logarithmic function, and which leaves dv as just being dx. And du would be 1 over x dx. And the antiderivative of, I guess there's just a 1 there. So the antiderivative of that would just be x. And now we get to use the formula. So u times v, so ln x times x minus the integral of v, which is x, du. And du is 1 over x dx. And if I tidy that up a bit, so that's x ln x minus x times 1 over x, that cancels. And so we get the integral of 1 is just x, and then a plus c, and that is the antiderivative of ln x. And this will be the last one we check using the derivative, but this is just kind of satisfying to do this. So let's just make sure it works. So the derivative of x ln x, product rule, 1 times ln x plus x times, I love that the derivative of ln x is 1 over x, because things just cancel nicely. And the derivative of x is minus 1, and the derivative of c is 0. And we are left with, so this is 1 minus 1, we're left with ln x, which is our original integrand. So now we're going to evaluate a definite integral using integration by parts. And the modification is pretty straightforward. If you would like your upper limit to be b, lower limit to be a, then since this part is already worked out, we would have to evaluate that from a to b and evaluate this integral from a to b. So again, u has to be this inverse trig function because we don't know its antiderivative, although once again you'll see by integration by parts that it could be derived. So dv will just have to be dx again. That the derivative of inverse tan x is 1 over 1 plus x squared dx, and v will just be x again. So we would do u times v, so x tan to the minus 1x, and of course we're going to evaluate that at 0 and at 1, minus the integral from 0 to 1 of v, which is x times du, 1 over 1 plus x squared dx. And if we evaluate x tan to the minus 1x at 1, that would be 1 times tan to the minus 1 of 1. Now you can see that if you plug 0 in there, it would just disappear. And inverse tan of 1, the angle whose tan of 1 is pi over 4. So now let's just tidy this up a little bit. And I'm hoping that you realize we have to use U-substitution for this integral. Well, since we already used u, we can always use another variable. It doesn't always have to be u sub. We could make it y sub. So we would make y in place for 1 plus x squared. And then dy by dx would be 2x. dy would be 2x dx. And it looks like here, we're going to we need to kind of figure out what x dx gets replaced with. So I might just isolate x dx and bring the 1/2 with the dy. So, so we are going to have the integral of, 1 plus x squared on the bottom, so that will become 1 over y, and replacing x dx with half dy. Now what we do need is the limits, so converted to y. So the upper limit when x is 1, y is 1 plus x squared, which would be 2. And the lower limit when x is 0, y is 1 plus 0, which would be 1. So these convert to the limits 1 to 2. And then we could just continue. So the integral of half 1 over y is just half ln absolute value of y. And that's from 1 to 2. And so we get pi over 4 minus a half ln 2. And then if ln of 1 is 0 anyway, so that disappears. And this is our final answer for the definite integral. Okay, so let's now evaluate this integral. So here's our formula for integration by parts. And our first decision is what should u be and dv. Now recall from earlier in the presentation that this is the order in which to choose u. U should always be logarithmic or inverse trig, or if neither of those, then A for algebraic. And I see an x squared there, so I'm already anticipating algebraic. Making u the exponential function is the last, right? The last of the options. So we are going to go for u equals x squared, which means dv is e to the 2x dx. And therefore du is 2x dx, and v will just be, so the antiderivative of e to the 2x will have to be half e to the 2x. So diving right in, u times v, so this times a half e to 2x, minus the integral of v du. So 1/2 e to the 2x times 2x dx. So let's tidy that up a little bit. So half x squared e to the 2x minus, well, as you can see, sorry, the 2's cancel. This integral has simplified, right? From x squared e to the 2x is now x e to the 2x, but you see it's not simple enough to do without using integration by parts again. So we are going to have to take this equation here. Let's see. So again, u should be the algebraic function, and that's going to leave dv to be this part. So let's put those in. So u is x, and dv, once again, is e to the 2x dx. And that leaves us du. Well, now that simplifies down nicely. So du is just dx, and v is once again half e to the 2x. So moving right along, e to the 2x minus. Now I'm going to kind of just create, I don't know, like big parentheses here to deal with the integration by parts applied to the integral. So uv, so x times half e to the 2x minus, we have another integral, the integral of v du. So half e to the 2x. Mercifully, there is no x in there, so it's going to be a little easier. That integral, we don't have to use integration by parts again. A lot of writing things out over and over again. So let's see, minus a half x e to the 2x minus, so minus will make a plus, and then we have a half times the integral of e to the 2x, so that will be 1/2 e to the 2x again, so it's going to be 1/4 e to the 2x, and don't forget that constant. And if we wanted to, we could really such a messy expression, but if we factored out a quarter, and we factored out e to the 2x, we'd be left with 2x squared minus x, and minus 2x plus 1, and then we have that plus c. And I'm not going to check this now, but you could check by finding, by applying the product rule, finding the derivative of that. It's a little more efficient than finding, taking the derivative of each term here. Anyway, if you took the derivative of that, you will indeed get back to the integrand. So this last integral is going to involve a little bit of a twist, so get excited. In terms of choosing what u should be, remember the order. So technically u should be a trig function before it's an exponential function. So I'm going to make u equal to sine x and dv equal e to the x dx. But I have done it the other way. So when you're sort of between those two functions, trig and exponential, they're somewhat interchangeable. So if you want to practice this, do some extra practice, you could reverse that and make u e to the x and dv sine x dx, and you'll find out that it will work out. But I'll leave that up to you. So that makes, let's see, du will be cosine x dx, and v will be e to the x. So diving right in, uv, so e to the x sine x, minus the integral of v e to the x du, which is cosine x dx. Now, you see the integral we're left with is by no means simpler, but it isn't more difficult either. It doesn't feel like we're really getting anywhere. When you feel like you're not getting anywhere, just try doing integration by parts again. So let's do that. So this time we'll make u equal to cosine x, and dv once again will be e to the x dx. So du is negative sine x dx, and v will be e to the x again. So e to the x sine x minus, and then I'll have a big old parentheses here. So uv e to the x cosine x minus the integral of v e to the x du, which is negative sine x dx. So let me tidy that up a little bit. Minus e to the x cosine x, and then minus, still minus. Wow, we really are going around in circles, it seems, because we're back where we started, almost. Now, if we notice, though, this is interesting, the thing that we're trying to find, we have that same expression, that same integral on the other side here. So if we actually just add that to both sides, we'll get two integrals of e to the x sine x dx. This is the trick. Equals e to the x sine x minus e to the x cosine x. And because we have no more integrals that we actually have to carry out, we need to include a plus c there to say that we're almost done. And the last step is to divide by 2. Sine x dx equals, I will factor that e to the x out because it just looks neater. Divide by 2, and you could divide the c by 2, it just becomes another constant, which we can just call c again. And that's our final answer.
So well done for making it to the end of the video. Here are 3 problems involving U-substitution for you to try. If you put the answers in the comments, I'll be sure to let you know if you're correct. And please do subscribe to my channel, Ready to Derive, and check out some of my other videos. Thank you.